So this question then is talking about roots of unity, specifically primitive roots of unity. To understand what these mean, I think just looking at all the examples is probably the best thing to do. So of course, if n is one, then we're looking for a to the one to equal one, and that's just one, right? That's the only first root of unity, I guess. One to the power one is one. Now, if n is two, we're looking for complex numbers such that a to the two is one. Now we of course know the answer to that, plus and minus one. So we put those in our roots. However, what this primitive idea is talking about is it's saying that 1 is not here a primitive root, a primitive second root of unity, because it's also a first root of unity. So this column here is going to be my primitive root of unity, and it's only going to contain here minus 1. I'll just continue with the n equals 3 and 4 and 5 first, though, for the actual roots. Now, if you've done the complex number chapters, this should be fairly clear. You always just think of it as 2 pi ik, and then just divide by the nth root, the 3 in this case, and then just set k to be 0, 1, or 2. So you're going to end up with e to the 0, which is of course 1. 1 is always going to turn up. E to the 2 pi I over 3, that's where k is 1, and 4 pi I over 3, that's where k is 2. That's just always how that's going to work. So likewise for 4, it's just going to be the same, but with a 4 underneath, and of course you end up with more because now you set k to be 0, 1, 2, or 3. So you end up with all these. I'll simplify these as well in a second. So 5 ends up being very similar, and 6 likewise. Now for the primitive roots, or like I said, maybe actually we'll simplify this a little bit first. You can think about these in terms of pi I over 2. Pi over 2 is over here, or you can think about which of course is I. So this one is I, and this one ends up being minus I, and this one is minus 1, of course, because it's e to the pi I, which is famously minus 1. Or you think of it in terms of being these polygons. Of course, the nth roots of unity make polygons around the unit circle. In this case, a square going from 1 to I to minus 1. Sorry, to minus I to minus 1. Oh, the other way around, whatever. And we end up with these lists here. Now, it might be easier to write these lists, and this is likewise going to be a hexagon, so it's fairly nice, and you end up with some more simple ones and some aren't, right? The only simple ones are going to be the 1 and the minus 1. The others I'll just leave as they are. The reason that I probably want those there, though, because it makes it slightly easier for me to spot the primitive roots, which is what this column is talking about. So for primitive roots of unity, of course, this is 1 because it hasn't turned up before. This one is only minus 1 because this 1 turned up in the previous one. This one, the 1 has, of course, turned up before, so it's not primitive. So these two are the primitive roots, and so on. So we can complete our table looking like this here. A lot of those from the 6 turned up before. And the 3, of course. The fact that those are multiples of each other is, of course, not a coincidence. Anyway, now we have our last column. And what's the last column for? Well, it's this new definition here of let Cn of x be the polynomial such that the roots Cn of x equals 0 are the nth roots of the primitive nth roots of unity. So, for example, this polynomial here is just the polynomial that has 1 as its only root. Well, that's just the polynomial x minus 1. And likewise, this one here is the polynomial that has minus 1 as its only root, which is x plus 1. And this one here, maybe the next easiest one to think about very quickly, this is the polynomial that has I and minus I as its roots, which is going to be x squared plus 1. I will proceed in order, though, because it's probably easiest to go in order. Let's think about this, how we can generate this n equals 3 one, though. So n equals 3, of course, if we're solving that, it's going to be x to the 3 minus 1 equals 0, because essentially we just want where we want the roots of unity. Of course, that would be x cubed equals 1, right? So we're looking to factorize x cubed minus 1, maybe. Of course, we know that 1 is a factor, so of course it must have this factor x minus 1. So there, of course, we can, well, I've crossed it out because it's not going to matter to our polynomial because we've already got that polynomial here. But to generate this one here, we'll do this a ton of times, but it turns out if you've got a number like x to the n minus 1, you can always generate polynomials that look like these. If this is odd, by the way, it looks precisely like this. If it's even, of course, it ends up being a different 2 squares and looks slightly different. But in any case, or at least slightly different in some other way, you end up generating this. Of course, you could polynomially divide to find that, or you could just spot coefficients and expand and make sure it works. But you do end up with this thing left over. I just always expand. You might also just know the because this turns up in step questions all the time, right? The factorization of a cubic, or a difference of 2 cubes, turns up a lot. So yeah, if you already knew it, then that was great. Anyway, because this one is already a primitive, or being used in this one here, it's not primitive, so therefore this is the polynomial we're looking for. Likewise, for n equals 4, you could do the same thing. Of course, this is a difference of 2 squares, but you could also have just, like I said, spotted that it's just going to be the expansion of x minus 1 into x plus 1, which is x squared plus 1. For n equals 5, same kind of thing as n equals 3, right? Same kind of thing here. We're moving on to the next part of the question, by the way, because we just found C4, which was this one here, which I already discussed. But the next one is C5 and C6. So we, of course, factorizing this thing here. We know x minus 1 is a solution. It factorizes to the same kind of thing that 3 did. Again, you can very quickly expand this to double check that it definitely works, or you could just do polynomial division on this to get this. It's kind of up to you. We don't care about this bit, of course, because it's already turned up, and we end up with this here. And then finally 6. You could do a difference to 2 squares here, or you could just follow the same pattern we were looking at before, and then follow it again, I guess, because you know really that this one's got to turn up as well, because we've crossed it out here. So it must have already turned up. So this one must be here somewhere. So you could divide this by this if you wanted to and leave behind this. And this looks about right. Except it's not, of course, because we already discussed that we're getting rid of these two roots means that this one must turn up. So that one must turn up. And then again, we could polynomial divide if we want to, or we could times out. It's kind of up to you. We end up with this one here, though, as our last bit that's actually not turned up before. Cool. Or you could expand out things like this, right? Because you know the only two roots of this, you know it must be a quadratic. The only two primitive roots, I should say. So we could just write these out, or we could expand it, we could add them up, and this kind of thing. Yeah, just adding the powers when you times them together, of course, and it ends up being okay. Probably an easier way, but it was nice to have a system that was the same as all the previous bits for that bit anyway. Find the value for n for which this happens. So we want 4 primitive roots. 5 has 4 primitive roots, but it didn't create this one, so that's a shame. If we obviously can't see it yet. If we go to 7, then, well, when we write out the 7th root, of course, it's just the same as what we're doing before, but with 7s everywhere. We get rid of this one because, of course, it's not primitive. And all of these are primitive, of course, because 7 hasn't turned up yet. And these can't cancel to anything like these because, of course, 7 is prime. But that's 6 primitive roots, right? And we can't have 6 primitive roots. We want 4 because the polynomial is degree 4. So it can't be n equals 7. So we go on to n equals 8. And we end up with this thing here, of course, just putting 8s everywhere. We cross out the ones that aren't primitive. You could simplify them down first to allow you to spot the ones that aren't primitive. It turns out to be a lot of them, of course, because 8 draws this octagon around the complex plane, of course. You're going to meet a lot of the things that you met with these previous even numbers. We end up with these 4 here. So that seems pretty good. Worth investigating 8 further because we know we have 4. Like I said, you draw this octagon that I was referencing in my head. That gets rid of those 4 which have already turned up. That gets rid of the 4 on the up and I minus I plus 1 and minus 1. You're left with these 4, which are here. Now you could just put those in a bracket: x minus this, x minus this, x minus this, x minus this, and expand out. It will turn out into being this. Or you could just deal with x to the 8 minus 1 like we were doing before. Factorize it. It's a difference to 2 squares. You could also just take out the x minus 1 and then the x plus 1 and so on and do it very slowly. But difference to 2 squares is probably slightly faster. It was kind of what I was referencing before. We can cross out these entire objects because this one just turns up here, and this one is a combination, of course, of those two things there. And we end up with the x to the 4 plus 1, which is done. And then the very last bits of the question then, given that p is prime, find an expression for Cp of x. So if we look at all of our prime examples so far, we have this one, so 2, 3, so let's write down the Cn's for n is prime that we have so far. We found all of those, and of course we can spot a pattern here, right? It looks like for Cp of x, we're just going to start one lower than p and then just work our way down with coefficients of 1 every time. And that seems like it's roughly it. But we should probably prove that it's this, or at least justify, give an argument for why we can definitely carry that on. And it's to do with this whole dividing by the number thing when we were coming up with our roots in terms of e. Of course, if n is prime, then we're going to be dividing by a number we haven't divided by before, and it's never going to simplify because it's prime. So therefore, it's never going to turn into any of the ones we had before. And so some kind of argument like that is, I think, pretty much all you need to say. And that will be pretty much that. So then we get to the last bit of the question. Oh, of course, and then if you wanted to, I guess you could argue that xp to the minus 1 just factorizes to this. That would be another way of just saying it, because, of course, you know you must have a root of 1. Of course you must. It's just always going to be there. And then you could prove that this divided by this is this if p is prime, I guess, with some polynomial revision, or just show that this expands this. Or, well, it doesn't matter if p is prime, right? What matters is that this won't factorize if p is prime at all. And so Cp of x equals that thing there. But again, that argument comes from this thing here anyway. So I think that's probably fine. Then it says prove there are no positive integers such that CQ of x equals CR of x, CS of x. Okay, so we're going to do a proof by contradiction here. We're going to show that, I don't know why I wrote that out again. Cool, whatever. We're going to do a proof by contradiction. We're just going to show that, we're going to suppose that it is the case and then just show that we get a contradiction in both in either way. So we're going to let A be a primitive qth root of unity. By definition, this must be true. That's just the definition they gave us for C of x. If A is a primitive qth root of unity. Okay, so then, but that means if we put in A everywhere, we get this is 0 because of this. So 0 equals this times this with A's in there. But that means, of course, that either this thing is 0 or this thing is 0. But if those things are 0, then that means that A is an rth root. Well, that means either, if this thing is 0, that A is an rth root, as a primitive rth root of unity, because, of course, it's going into C, and C, the polynomial C had to do with primitive roots. But if A is a primitive primitive rth root of unity, and it's a primitive qth root of unity, then that means that Q and R must be equal, because otherwise that just can't be the case, right? So Q and R must be equal. But if Q and R are both equal, then going back to this line, then Q equals R means that CS of x equals 1. But this polynomial can't just equal 1, because for whatever s you have, e to the 2 pi over s is always a primitive root. It always makes it equal 0. And you can look back at all the examples we had, but like when you had n equals 4, in this case s equals 4, the first, or the second root after 1, I should say, of 2 pi over 4, that was a primitive root. And then the next one, 2 pi over 5, and the next one, 2 pi over 6. It has nothing to cancel with above it. And so therefore it's always a primitive root. So these CS's, or CNs of x, always have at least one root, the kind of initial one. And so therefore it can't just be the polynomial 1, right? Like it definitely has a root somewhere. So that's a contradiction. And then over here, actually, it's just the same argument. You just swap R and S over, and you make exactly the same argument. And we're done with the question. So another complex number question here, all to do with points on a circle. So let's just get some drawings out, see what we're looking at. So we've got a bunch of complex numbers, maybe on a circle radius A at the origin. So imagine an x and y axis going this way, I guess, or a real and imaginary, I guess you should probably say. Got P, Q, R, S all on there, so that's good. Representing complex numbers P, Q, R, and S, little P, Q, and S, I guess. And okay, show this thing here. Well, classically, we're going to start on the wrong side. We're going to start on this side first. The equation of a circle centered at radius A, centered at the origin, is just z bar equals A, or mod z equals A, of course. I'm just saying the distance from z to the origin, z minus 0 to the origin, is A. But mod z, we could, of course, write, if we want to, or if we just square both sides like that, we get mod squared z squared equals a squared. And of course, mod z squared is equal to z star, right? Because I'm looking at this and I'm thinking, well, we need stars somehow, right? We need stars. Let's relate this to the stars, to the conjugates. So okay, z star equals a squared. But of course, we can just put in the information, because we know that P, Q, R, and S are all on this circle. We can just put in the information, therefore, that P star equals a squared if it's on the circle, and likewise for Q. Right, so we get this information in here, and now we're ready to start on the right hand side, because we can just throw those results into here, because if we times everything by a squared, or just move that a squared into the result like this, a squared p is the same as just timesing this by p both sides, so it becomes p star p, and likewise for a squared q, right? So that's cool. A squared. Oh, but I've actually replaced it. This is intelligent. If you replace it the wrong way around, right? So if you replace the QQ starred into there, so the wrong way around by putting the QQ star into that one and PP star into that one, then you end up with a term that you can then just factorize out the PQ, right? And then of course you have this minus this over this minus this. Well, that's just the wrong way around. So factorize this to be the other way around by putting the minus out here, by getting rid of that minus essentially. And you can make them the same, and then you can cancel them out, and we end up with 0. We end up with just the PQ times 1, or just PQ left over. So yeah, kind of a tricky start to the question, but let's continue. We have to deduce that if the chords are parallel, then PQ plus RS equals 0. So okay, what do we know if the chords are, parallel? Perpendicular. Show that this is 0. So what do we know if they're perpendicular? Well, what we can say is that PQ minus Q equals IK lots of I R minus S. Now, what does this mean here? Well, P minus Q, think of complex numbers as just being like vectors, right? This P to Q as a vector is just p minus q, right? You're going to p, then you're going back to q, so it's just p minus q all the way around. It doesn't really matter, as long as you have the other one, I guess, the other way around. Now this I here, all that's doing, remember what happens geometrically when you times by I? It's just rotating 90 degrees. So this whole perpendicular idea we can compress into just this idea of timesing by I to rotate it around. So p minus q is this vector, r minus s is this vector. If we just rotate this one around 90 degrees, we'll get to this one because they're perpendicular. This k is also saying that you can stretch it and squash it as much as you want, as long as you've got that rotation of 90. If you imagine moving this r and s quite close to each other up here, of course the vector pq is much longer, so you're just compressing it with a multiplier k, which doesn't really matter. Okay, now we can also come up with a very similar expression for p star and q star, because of course all these are the conjugates. If you imagine p star is just down here somewhere and q star is up here somewhere, and if you do the same with all four, they're still going to be perpendicular, so we can still come up with a relationship that looks very similar like this. And now if we actually start using this idea here, we're trying to show that this is 0, but we're ready to start putting in some results, I think, because we can put in the result from the first bit. PQ is of course this, RS is of course this, pretty standard to use that. Of course I didn't really mention, but I just said RS was the same kind of thing as this, where we just have the numbers R and S rather than the numbers P and Q. It must just be the same, right? So we end up with this here. We can of course factorize out the A squared, and then we're ready to start putting in these results, right, into P and Q and into P star minus Q star here. So we can put in these two results. We can cancel out some RS's. Sorry, some IKs, and then you notice that the bracket is just cancelling itself out. So the whole thing equals 0, which is what was being asked for us to get. And now we're actually into the last bit of the question, which is cool, although it is the longest part of the question. Suppose you've got a bunch of points. We'll start with n equals 3, since it's the most simple. On a circle, we've got a bunch of points, B1 to B2, B3 on a circle as well. And apparently, if you connect A1, A2, and B1, B2, and B2, B3, and A2, A3, and so on, it's looking for them to come up with a bunch of perpendiculars. So A1, A2 is perpendicular to B1, B2. This picture isn't amazing, but it looks like it roughly could be. And then A2, A3 with B2, B3, again, could be. I mean, this is just hard to draw, right? But that's the idea they're going with. It's hard to actually find an example that works in a reasonable way, but we don't really need it, so that's okay. So A1, A2 perpendicular to B1, B2, of course means that it's got to follow this rule here, right? So we can say that we can just apply this rule, and we can say that means A1, A2 plus B1, B2 equals 0. That's just applying the rule that we proved in the previous part. But likewise, you've got to say that's true for A2, A3 as well. So we'll shove those results in and we'll get this. And it's also got to be true for the third lot, which is, notice the last step is going Bn, B1, and An, A1. So that's going to be, in our case, A3, A1, and B3, B1, right? So that goes in there as well. So this is a three-dimensional simultaneous equation. Doesn't seem too bad. What we could do is we could just move some stuff over, of course, and then we could times the results together. And then we could do, if we move the last result over as well, and then combine these together, replace this B2, B3 object with these minus A2, A3s, and we end up with this here. Cancel these things out with a minus, I guess, as well, and we end up with minus A1 squared is equal to B1 squared. So there are two things that B1 can be, plus or minus I A1. And that's kind of nice. So for n equals 3, there are only two choices for B1. Well, there are the two choices. You just set it to plus or minus I, and then whatever A1 was. What is the corresponding result for n equals 4? So again, this picture is kind of irrelevant because it's almost impossible to draw. But anyway, we'll go straight into here and we'll start using this result a bunch more here. So we're going to have to do this for 4 results here. I'm going to rearrange all of them like this first because that ended up being quite relevant for the previous bit. Now for here, we might be able to spot a trick, which is we can actually just multiply all of these together because there's actually precisely 2 of everything, it looks like. So everything just becomes squared like this. There are also 4 minuses over here, so they all cancel out to give me this here. Now at this step, we can start replacing certain things. So for example, I mean, we need to rearrange for B1, right? Because it's talking about B1. So divide by all these B2, B3, B4s and so on. But if you look at this, of course, you've got expressions for B2, B3 right here. That's minus A2 squared, A3 squared. So that middle 2 things will cancel straight away like this. And we'll end up with this here. Now, what does this imply? Well, of course, if you just choose all your A's to be something, then this means that B1 is just dependent on whatever you picked B4 to be. But of course, that means you can just pick either of them arbitrarily, and then the other one just gets set, right? So you put all your A's down in wherever you want, and then as soon as you picked a place for B4 to be, that just gives you a place B1 needs to be. But of course, you can change that B4 point wherever you want, and B2 and B3 apparently don't even matter for it. So this can just be picked arbitrarily, and we'll have any number of results we want. And then it says state the corresponding results for n greater than 4. So it's interesting that in the two cases we have, for n equals 3, we only have two answers. It was plus or minus this thing here when n was 3. But when n was 4, you had an infinite number. So maybe it's an infinite number forever, or maybe it alternates between having two answers and an arbitrary number of answers and so on. So that's kind of either one. And the answer comes from looking at the working that we did here. If we look at the working that we did, it helps us out, because what we can do is we can come up with a general case here, where if we have an even number of, where n is an even thing, and what we can say is, we're going to come up with, when we write all these equations out, this is just saying that a1 and a2 are perpendicular to each other. Sorry, a1, a2 is perpendicular to b1, b2, and so on. We end up with a bunch of equations, precisely 2m of them, right? And they're all rearranged over here with the minuses on the other side, just like I did for the previous one here. And now, just like I did for the previous one, let's just multiply all of them together. Of course, if 2m is of course even, because it's got a 2 there, which means all those negatives are going to go away. So that's cool. And then when we divide by all of these b's that we don't want over here, what's going to happen is there's going to be a whole bunch of cancelling. So a bunch of pairs here are going to cancel out. Now, because 2m is even and you're missing the first term, there's an odd amount of b's here from b2 to b2m because b1 is missing. So that means when these cancel in pairs, you're not going to cancel the very last one out. You're just going to cancel them up into pairs up to the very last one, which means you then get left with this here. And then, of course, that means that we're in the case we were in before, where we can just arbitrarily choose a b2m, and then we get b1 with whatever we want. And then, of course, when n is odd, we do the same thing where we write them all out. We're going to write down an odd number of equations here. So therefore, when we write down an odd number of equations and multiply them all together, we're going to get a -1 in front. But actually, kind of more importantly, down here, of course, because 2m plus 1 is odd by definition, that means when you're missing b1, there's actually an even number of things down here, which means when you cancel them all out in pairs, like we've been doing before, they just all go away. And we're left with this here. We can root it if we want to. But in any case, we're going to end up with two choices for b1, and that's going to be the question done.